In the complex and interconnected world of electrical power systems, few concepts are as fundamental yet as often overlooked as power system angles. These angular parameters, phase angle, torque angle or load angle, and power angle, serve as the vital signs of a healthy, stable, and efficiently operating power grid. While they may seem like basic textbook material on the surface, their implications are profound and far-reaching, influencing everything from individual generator performance to system-wide stability across entire transmission networks. Understanding these angles is not merely an academic exercise, it is essential for grid operators, system planners, and electrical engineers who must ensure the continuous, reliable delivery of electrical energy to millions of consumers. Phase angle. The local power relationship. The phase angle, typically denoted by the Greek letter theta, represents the angular separation between the voltage and current waveforms at a specific point in the power system, a single node or measurement location. This angular difference is measured from the zero crossing point on the horizontal axis of the waveforms and indicates whether the current is leading or lagging behind the voltage. For this measurement to have practical significance, both voltage and current must be measured at the same node and must operate at the same frequency, non-negotiable requirements for accurate phase angle determination. The phase angle is directly linked to the concept of leading and lagging, which arises from the reactive power characteristics of different types of electrical loads. Capacitive loads cause the current to lead the voltage, as capacitors inject reactive power and push the current waveform slightly ahead in time. Conversely, inductive loads, such as motors and transformers, cause the current to lag behind the voltage, as they consume reactive power and create a delay. This phenomenon is fundamentally driven by reactance, the opposition to current flow caused by capacitors and inductors, which differs from resistance in that it shifts the phase of the current relative to the voltage. In purely inductive or capacitive circuits, this phase shift reaches exactly 90 degrees, demonstrating the classic relationship between reactance and angular separation. The phase angle also appears in the context of power relationships through the power triangle. The angle between active power, measured in megawatts, MW, and complex power, measured in megavolt amperes, MVA, is mathematically equivalent to the phase angle between voltage and current. The cosine of this V phase angle represents the power factor, calculated as the ratio of MW to MVA. Whether viewed through the lens of waveforms or power components, the phase angle remains the same fundamental relationship at a single location, connecting local voltage and current characteristics to overall power efficiency. Core power factor, indicated by large phase angles, results in higher total current MVA for the same useful power MW, leading to increased transmission losses and reduced system efficiency.